I hope you can see my screen. Okay. And before that, let me. Okay. So before that, let me introduce myself. Okay. Yeah. So I'm Balram Shah. I'm the PMRF TA for this course. That is Watershed Hydrology. So we'll directly jump into the present PPT first. Let's see. I have shared the screen. Okay. So which subject we are studying right now is watershed hydrology, right? So uh, in this session, what you expect is, what I'll explain are the a kind of summary of whatever you have studied in the respective weeks. Such as in this week, you have studied around 5 lectures, which I will summarize, and there will be week each week assignment will be there. So I'll be giving some tutorials on some kind of assignment questions, not the questions that you are getting in the this week, but similar kind of questions which will help you to finish those assignment easily. Okay, so I will be going through some of the assignment questions and so on. Okay, so this is the week 1 lecture or the week 1 tutorial session for the watershed hydrology. I am Balram Shah. I am the PMRF TA for this course. I am doing my PhD at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. That is ISC Bangalore. Okay, so with that, let me start. Firstly, I'll not go to the questions directly, but I'll give a small brief introduction. And yes, this session should be an interactive session. Okay, so it's not like a class that I am just giving lectures and you guys are listening and that's it. Okay, so I'll be giving some questions and I'll expect you to interact with me so that whatever doubts you have or whatever doubts you have regarding when you are seeing the lectures, it should be cleared in this. So that is the main aim of this tutorial. Okay, so if anyone can introduce themselves, they can, or if they don't want to speak, they can write in the chat box so that I can know if they want. Okay, so I'll stop the sharing here. I'll start the presentation from this side. Uh, okay, give me a minute. I'll join it from here. Okay, I hope you can see this screen. I'll switch off the video so that it will be easier to download. Okay. I hope you can see the screen, right? Anyone can give thumbs up or something so that I can know if you guys are seeing the screen. Yeah, okay. Thank you so much. Okay, so the subject is watershed hydrology. Before going to what we are going to discuss in this course and why we are studying this course, we should understand what is the each of the terminology in the course name means, right? So first one is the watershed. Okay. So the first one is watershed, right? What do you mean by watershed? Anyone? So watershed, let's say, so if you go by definition, it is an area of land that drains, or you can say sheds, all the streams and rainfall to a single outlet. Okay, so let's say if you have an area in which you can have mountains, you can have hills, you can have valleys, you can have ponds, and so on, right? So let's say there is an area like this. Okay, now let's say a mountain is like this, maybe. Okay, now any rainfall which is coming on this area will flow in this direction, right? And it will join one stream, and then there will be a main stream and there will be an outlet. So like that, if I draw it properly. Oh, sorry. Can't do that. Shit. So I have to write it again. That drains or sheds all these streams and rainfall into a single outlet, right? So it can be an area like any rainfall, any water which is falling in that area. What will happen? It will go and join the main stream, and then it will have only single outlet. Okay, so let's say if this is the outlet at this point, and this is the main area, there can be several small streams. Again, these small streams can have smaller streams, which have smaller streams. So like that, now you can say this can be one main big stream for one. So this can also be considered as the sub watershed or sub catchment, let's say. So it is also considered as a water. So this watershed is also called as basin, or it is also called as catchment, just where we are using in the, maybe in US or something like that, right? So from this one of the word called basin, right? So in every household we have one wash basin where what we are doing, we are washing our hand, or let's say something whatever we are doing. In that, wherever you put the water, it will go and it will go to the outlet point, or it will go to the sink, right? So that is why it is also called as a basin. Okay, so that is watershed. And second terminology is hydrology, right? What is hydrology? Hydrology has two words in it. That is hydrology and logy. So that is the study of water, right? So hydrology is defined as the study, or let's say science, which deals with the occurrence, circulation, distribution, and the characteristic properties of the water. Okay, so let me write that. Is the science or study dealing with the occurrence, circulation, distribution, and properties of water of the earth and its atmosphere. Okay, so hydrology, there are different definitions. So overall, I found this definition to be having all the definitions that we have seen. So it will deal with the occurrence as in how the water comes into the atmosphere or the land surface or the earth. Then circulation, how it so we know that water is always in a flux, right? So how it circulates in the atmosphere or through the earth atmosphere and below the earth. Okay, then distribution of water, properties of water of the earth, and so on. So with this, I hope the terminologies are clear. Okay, now what is this hydrology? That is clear, right? Next, hydrology deals with the hydrological cycle. We all have studied hydrological cycle in our schools and all, right? So what is hydrological cycle, anyone? And firstly, why should we study this subject, that is watershed hydrology? Why should we study watershed hydrology? What we'll get after studying this subject? Anyone? Okay, so after studying this subject, what we should know? We should know the basics of hydrology. What are the hydrological components? Hydrological components are the components which are present in the hydrological cycle or on the earth, let's say. Yeah. So we'll be studying about hydrological components, watershed hydrology, hydrological components as in precipitation, interception, infiltration. So there are several hydrological components which we'll study. In those components again, how it happens, why it happens, and then how we can measure those, why it is important, and what we can do with that. Okay, the impact or how we can use those hydrological components for the betterment of the society, let's say. Okay, then we'll study each of the hydrological components and very detailed into all the hydrological components. Then we'll be studying about hydrological modeling. Then we will also studying about the geomorphology as in the drainage basin characteristics, like what are the dimensions and all. Then we'll study about hydrological modeling, as I said, then calibration, validation, sensitivity analysis. So recently or in this world, we know that there are kind of extreme events that are happening, such as floods are happening, extreme rainfall, then droughts. So we'll study all these throughout our lectures. Okay. So like that, we'll study all the hydrological components and so on. Okay. And we all know that water is a very important for our life, not only for our life, for our economy, society, and so on. Right. So I'll not go very detailed into that because we all know that out of the 100% of water, around 97.5% is salt water, and remaining whatever 2.5% are there, that is fresh water. And in that 2.5% water also, around 69% of water are in glaciers. Remaining again 31% is in let's say groundwater, and the remaining are in the lakes and river storage. And that is why, because the glaciers and all, we don't have that much of accessibility. So in what things we have accessibility? First one is the lakes and river storage, and then second one is the groundwater. So that's why in recent decades, as water demands are increasing, what we are doing, we are extracting the water from the ground itself. And from there also there can be several problems that are happening. So we'll study that in the later weeks or later lectures. Okay. So we have ample amount of water, but as we know that as our population is increasing, our land area which we are using are increasing, and hence the water demand is also increasing, right? So with this I'll start. So we have hydrological cycle. So we know that in hydrological cycle, what all will be there? There will be hydrological components. So let's start from because it is a cycle, we can start it from anywhere. Mostly what we do is we start from the precipitation. So let's say let's say you can start from the evapotranspiration or evaporation. So let's say you start from the precipitation which is coming on the ocean. Okay. So what will happen? Precipitation is happening. Okay. And which the water that is coming, it will go in the form of evaporation and transpiration that will come. Now evaporation is whatever water is there that is getting evaporated back into the atmosphere because of the temperature, as in solar irradiance and so on. Okay, then transpiration which is happening from plant, then the remaining water which is going as the stream flow in the rivers, then some water which is getting intercepted below the groundwater, then okay, below the groundwater, interception will be there. Then there will be some storage of water that will be left from one time to another time. So that also we'll discuss in the later slides. So first one of this hydrological cycle is the precipitation, from where we get the water that we need. So we'll be focusing on precipitation in today's tutorial, and then how we measure this. Firstly, what is precipitation? We will know that. Second, that how we can measure the precipitation, or we'll be mostly studying about rainfall, why rainfall will come, then how to measure, then what we can do after measuring the rainfall, and if there are any missing rainfall data, how to interpret that and how to get to that, and so on. Okay, so this precipitation can be divided based on several classification. It can be rainfall. So what is precipitation? Anyone, what is precipitation? So many a days, many a times we use rainfall as precipitation. So whether this rainfall and precipitation are same or not. So precipitation is like any form of water that falls from the atmosphere. Okay. So let's say any form of water. It might be solid, it might be liquid, anything. So any form of water which are coming from the atmosphere to the Earth's surface is called precipitation. So most dominant in our location, let's say, it can be rainfall, right? So the form of which is in the form of liquid. So the dominant part of precipitation is rainfall. Then we can have glaze, we can have snowfall, then we can have hailstorm, and so on. Okay, there can be other classification also, like drizzling or drizzle, then dew, frost, sleet, and so on. Okay, sleet. We'll just see one by one. So rainfall, you know that rainfall occurs in the form of water. Okay, so the dominant form which is happening for the precipitation is the rainfall, and that is why we mostly focus on the rainfall. So it doesn't mean that we don't study about snowfall and so on. For glacier studies and all, we also study about the snowfall and how the glaciers interacts. So that is a separate part, but we are not going to study that part in details in this course. Okay. So what is this rainfall? So mostly we consider rainfall when the size of the drop varies from zero point 0.5 mm so to around 6 mm or more, let's say. Okay, so whenever the size of the drop which is falling from the atmosphere to the Earth's surface is varying between 0.5 mm to 6 mm or sometimes more, we consider that as rainfall. So any water or any liquid form which is coming from the atmosphere to the Earth's surface and is less than 0.5 mm, that we consider as drizzling. Okay, so that we consider as this drizzling. So drizzling is the form of water droplets which are having less than 0.5 mm in diameter, and intensity is, so I'm like 0.5 mm, and intensity is less than 1 mm per hour. That is called as drizzle. Okay. So how this rainfall occurs? The main basic fundament, the main basic concept is waters are moved away from the land and reaches the atmosphere to form clouds, and where this condensation happened. What is condensation? Phase change from the liquid phase, sorry, gas phase to the liquid phase, and that forms the cloud droplets at temperatures which are above the freezing point, and that comes as the rainfall. So this rainfall can be classified into, let's say, light rainfall, moderate rainfall, and heavy rainfall. Okay. So these, whatever I'm explaining, I'm not writing that much because most of that you will get in the lecture slides. Okay, just to summarize, I'll say what is a light rainfall. If the rainfall is having intensity, so here most of the time we talk about the intensity, right? So what is intensity? What is this word intensity? Whenever you hear this word, that is intensity, what clicks in your mind? It is kind of how intense it is. Oh, okay, or how fast it can happen, or what is the speed. So the unit for this will be millimeter per hour. Okay, so the light rain happens, or as I said, rainfall can be classified into three. That is, first one is light rain. When the intensity of rainfall is less than 2.5 mm per hour, it is light rain. When the rainfall is happening between 2.5 to 7.5 mm per hour, it is moderate rain. And when it is more than 7.5 mm per hour, it is called as heavy rain. Okay. So there are other parts of precipitation, that is, cloud burst can happen. Okay. Cloud burst can happen. What is cloud burst? Cloud burst is a sudden and intense rainfall. So suddenly one intense rainfall is happening, which is like a large amount of rainfall is occurring in a very short period. That is around 100 mm of 100 mm per hour rainfall has happened in a very short period. That will be considered as cloud burst. Then there can be snowfall, as I mentioned. Snowfall occurs in the form of ice crystals. So as I said, that any form of the water which is coming from the atmosphere to the earth's surface is called as precipitation, right? So this snowfall occurs in the form of solids or in the form of ice crystals. And this ice crystal is happening why? Because of the sublimation. In rainfall, what we have studied, that is mainly because of the condensation. When water goes above, and then we get the from the gas to liquid. Like that, in snowfall, we get sublimation. That is phase change from gas, or let's say water vapor, to the solid form. That is the ice crystal form. Okay, so that is called as snowfall. So tiny ice crystals in what happens? So these tiny ice crystals sticks together in the cloud to become snowflakes, and when enough crystals stick together, they become heavy and fall to the ground. Okay, so this is snowfall. Then drizzle we have studied. What is dew? Dew is like condensation of atmospheric moisture or the water vapor that forms as tiny water droplets. So you will see in the winter time, you will see that there are surfaces like grass, leaves, or other objects where you see small water droplets, which is considered as the dew. Okay, next is hail. What is hail? Hail is like hailstorm happens. If you would have seen, sometimes it happens that along with the rainfall, there are big kind of, well, let's say some ice crystals will be there, which are bigger in size. That is 5 mm diameter. So precipitation in the forms of lumps of ice, which are having over 5 mm diameter, formed by alternate freezing and melting, is called the um, what? Hailstorm. Okay. Next is glaze. In colder places, you will see. In colder places, you will see that there will be ice coating on the raindrops. Okay, while they come in the contact with the cold objects on the ground. So that is called as the this glaze. Okay, and this fog, you know that in winter season we can see that low-lying clouds are composed of several tiny droplets or ice crystals suspended in air near the earth's surface. That is called as fog. And then comes the sleet, that is frozen raindrops of transparent grains. So small grains will be there on the, or when this rainfall happens. And this happens when air is at sub freezing temperature. Okay, so that what is sub freezing temperature? Sub freezing temperature is the temperature just lower, or let's say colder than the freezing point. Okay, so with this we'll just see one question first. Okay, so the first question is which of the following process is a key component of the hydrological cycle? Okay, so in hydrological cycle we have studied so many hydrological components, right? So among this, what do you think is a basic key component that is present in the hydrological cycle? Anyone? Okay, so we have studied precipitation will be there, then evaporation will be there, transpiration will be there, then interception will be there. then stream flow, runoff, base flow, all these things will be there. So here you can see photosynthesis, cellular respiration or mitosis. These are not the part of the hydrological cycle. So answer will be transpiration. Right? So transpiration is what? The process from which water gets evaporated or gets back to the atmosphere from the um, plants or trees or something like that. Okay. So the correct answer will be B, that is transpiration. Okay, so the next question is when rain falls through air at sub-freezing temperature, it forms what? So just now I have mentioned that snow is what? Snow is like ice crystals when sublimation occurs and it falls as in the form of precipitation, that is snow. But that happens at freezing point, right? Or from from the gas to liquid it happens, right? Next is drizzle. Drizzle is when rainfall or for precipitation happens in the liquid form, but with a diameter or size of less than 0.5 mm. That is called as drizzle. But that also happens not at sub-freezing temperature. Glaze, you know, the thin layered, and the sleet happens when that small time crystals kind of structure, but that happens at sub-freezing temperature. So the correct answer will be sleet. Okay, answer will be A. Next question is which type of rainfall occurs when moist air is forced to rise? Okay, so before that I'll just explain what are kind of rainfalls. Okay. So, so as I said, the rainfall, this rainfall can be classified into several different types of rainfall based on how it happens. So rainfall can be cyclonic rainfall, or which we call as frontal rainfall also. Next is convectional rainfall, and third one is orographic rainfall, or we can call as relief rainfall. Okay, so the first one is cyclonic rainfall, right? So what is cyclonic rainfall? Cyclonic rainfall happens when, let's say, when any anti-clockwise rotation happens of air masses and which results in a low pressure in the center. Okay, so that is called as kind of cyclone or low pressure system, right? So because of that, what happens? Wind will converge to the center and it will be driven vertically upward to the like wherever at height where it is colder. Okay, and there condensation occurs, and as I said, because of the condensation, the gas converts to liquid, and hence the rainfall happens. So that kind of rainfall is called as cyclonic rainfall or frontal rainfall. Okay, so it covers around 2500 kilometer in diameter. It arranges, it's not a specific value, and its movement is around 50 kilometer per hour. Now, this in India, we face a lot of tropical cyclones, like which formed over warm water bodies, such as oceans, let us say Indian Ocean or South Pacific Ocean. Now, again, this cyclone is also called as hurricane, is also called as typhoon, based on where it is or based on regions. Okay, so hurricane happens when, or hurricane, we call it as hurricane when it happens in Atlantic Ocean or the Northeast Pacific Ocean region. Then we call it typhoon when it occurs in the now Northwest Pacific Ocean region. Okay, so these cyclones has been classified, or IMD as in Indian Meteorological Department has classified the cyclone in several form, that is, so like based on the what is the intensity or what is the movement of the wind storm, we call it as different cyclone, as in cyclonic storm, or it is severe cyclone, or it is very severe, or it is extremely severe, something like that. Okay, so let's say if it is cyclonic storm, so based on IMD, the movement of wind is around 62 to 87 kilometer per hour. So recently in India, so mostly the cyclone that we see are in the coastal region. And you will see some of the cyclones in some of the land joined areas also, but most of the cyclones that you can see is in the coastal region of the area of the earth. Okay, so recently you have seen cyclone Ramal. Again, this Ramal was there around in May 2024, maybe something like that. So this Ramal was a severe cyclone. So again this, so it can be severe cyclonic storm which is having a movement in between 88 to 117 kilometer per hour. So this removal happened in the states of West Bengal, Odisha, and all. And the movement or the speed for that or the intensity for that was around 110 kilometer per hour. Okay. So again, other than that, we had in recently in around November or December, we had one cyclone called Fengal, which happens near Tamil Nadu area, Tamil Nadu Pondicherry area, right? So that is also one kind of cyclone. Then one severe, extremely severe cyclone happened in West Bengal or Odisha, that part called cyclone Amphan, which was around 260 kilometer per hour. Okay, so that kind of that will also produce rainfall also. That is first classification of rainfall. Second is the convective rainfall or convectional rainfall. What is this convective rainfall? The convective rainfall occurs when the Earth's surface is getting heated and which will cause the air, because warm air will flow upward, right? So it will cause the air to rise rapidly, and this rising air will cool and condense at the colder altitude, and then it will result in precipitation. So this heating occurs mostly in the equatorial region or very near to that. Okay, and in India we get this kind of, that is convectional rainfall during pre-monsoon period. So when the Earth's surface gets very much heat and the air will rise very rapidly and it will condense and it will come as precipitation. That is the pre-monsoon rain that we are facing in India. Okay, so second one is the convective rainfall. Third one is the orographic rainfall, or we call it as relief rainfall. From the word you can understand that the relief should be changed. So this kind of rainfall occurs when the air masses are lifted as they move over mountain barrier. So let's say warm air is coming and it has some barrier, and because of the barrier it will rise up, and because of this rising up again it will happen, condensation will happen and it will come as a precipitation. So when these barriers are there, kind of mountain barriers and all, because of which the air masses will be lifted and then precipitation happens or the rainfall happens, that is called as orographic rainfall or relief rainfall. Okay. Any questions till now? If not, I'll move to the next question. Okay, so the next question is, which type of rainfall occurs when moist air is forced to rise over a mountain barrier, leading to cooling and condensation? So as just now I have explained, it is relief or orographic rainfall. Okay, so the correct answer is C. Next question is, what is the term for rainfall that occurs when warm or moist air rises, cools and condenses, and often resulting in thunderstorms? Right? Can you tell me the answer? You can write in the chat box also if you want. Anyone? So here what happens? The warm air or moist air will rise, it will cool and condense, and it will come as thunderstorm, or let's say the rainfall. So it will be convective rainfall or convectional rainfall, right? Next question is, how many types of rain gauges are there? Okay, so before that we'll just see what is this. Okay, now after we know what is rainfall, how it happens and all, we should measure the rainfall, right? So to measure the rainfall, we have instrument called rain gauges. Okay, so there can be different instruments. So these rain gauges can be defined or can be classified into two. That is, one is non-recording rain gauge and another is recording rain gauge. Okay, so this non-recording rain gauges is one of the example is Simon's non-recording rain gauge, right? I'll not go in detail much because we have seen that in the class. And one thing I'll suggest is, if let's say you are coming for the tutorial session, because it is around 5 lectures, 6 lectures will be there in 1 week. It will be very difficult to complete everything in detail in this tutorial session. I'll just go as a summary. Okay, so it's better that you first finish those lectures and then come, because you will have some doubts only if you finish those lectures, right? So here I'll help you to solve those doubts, or do some assignment questions and all. Okay, so let's get back to the recording gauges. Okay, so non-recording gauges where Simmons rain gauge will be there. So there will be one container will be there, and then one funnel kind of thing will be there in which rainfall will happen, and then it will go into one receiver kind of thing, right? So a vertical or cylindrical container will be there with top will be open, because the rainfall will happen, and it will have around dimension or the diameter of 127 mm. So a funnel shaped funnel will be there, so that the water will go. This funnel is so that such that it is because the evaporation is less. Otherwise, if we just keep one cylinder and rainfall is happening, we measure the rainfall, evaporation will also happen, so we don't know exact amount of rainfall that is happening, and that's why we have funnel, so that only small part of water, it's if it is evaporating, it will get evaporated. Okay, so standard time for recording in this non-recording rain gauge, that is Simmons rain gauge, is around 8:30 a.m. So every day at around 8:30 a.m., whoever is doing this measurement, they'll come and check the um, rainfall measurements. Rainfall measurements will be either in millimeters, centimeters, something like that, right? So again, they will throw the water. Again, in the next day, whatever rainfall is happening at around 8:30, they will again see, and every day they will get daily rainfall data. Okay, that one was non-recording rain gauge. Okay, so non-recording rain gauge one was Simmons non-recording rain gauge. Okay, in recording rain gauge we have siphon type or float type. Okay, so in float type, what will happen? There will be a siphon kind of thing, and there will be one float kind of structures. Okay, now again the one kind of lid or funnel will be there, where water will come, it will go inside, and then as the water level increase, that structure, that is which is floating on the water, will get up, right? Will go up, and at the maximum it will go, and again when it reaches the maximum, the water will flow through the siphon, and it again will clear the water, right? So in this, what is happening, you don't have to come and take a reading every time, right? So here whatever rainfall is happening after the maximum, it will get siphoned, and it will the water will get cleared again. And with this, there will be one chart will be there. Okay, as the rainfall is happening, it will get recorded in those chart, and then when rainfall will not be there, it will go again straight, and then again when rainfall is there, it will again start moving, right? So this is kind of, this siphon type or float type is most commonly used recording type of rain gauge. And there the measurement, that chart whatever I have said, there will be a one clockwork mechanism will be there with let's say daily or weekly chart. After 1 week or something, whenever this chart is full, people will come and you will change again, and similar kind of thing will happen. Okay, next we have tipping bucket type. Okay, so in tipping bucket, what happens? Rain falls, it will have a balance. Okay, I'll show something here. Give me a minute. Sorry. Stop sharing. I'll share here first. Okay, I hope you can see the screen. Right. Okay, so I was mentioning the tipping bucket type, right? Should open, I'm not sure. Okay. hope you have seen the video. So what was happening in that video? So water was coming through that funnel or lid, and then whenever it is around 0.5, so whenever it was around 0.5, it was it was tipping and it was getting tipped into the bucket again. It is happening in the second tips and it is going into the bucket. So in this tipping bucket, what is happening, that two containers on the balance, so there was a balance and there will be two containers kind of thing. It will form a tipping bucket, right? And when rain will fill in one bucket, it will tip over, and then second bucket will be and the water that has been tipped, it will be collected in another bucket, right? So the capacity of the bucket is manufacturer specific, where mostly it is around 0.5 mm. So a recording mechanism, usually digital or digital, will be there, which will record this data. So how many times it has tipped, it will record there, and based on that we can understand that how much of recording or the rainfall has been recorded through the tipping bucket. Okay. Next one is the weighing bucket type. So as the name suggests, that there will be one weighing kind of thing where, let's say, a spring balance or something like that. So how much amount of rainfall is coming, it will get weighted, and based on that we can know that how much amount of rainfall has happened. Okay. So the movement of the bucket will be because of the increasing weight, and it will be transmitted to a pen which will trace or the record on the clock driven chart. So there will be uh, like clock driven chart will be there for each of these kind of, so that's why it is called as recording gauges. Okay. And so we have also seen that there will be a gauge network or rain gauge network. What is this network? That how many numbers or rain gauges are there in a area. Based on that, there will be rain gauge network. So if, let's say, for one area we have a lot of rain gauge stations where we are measuring the rainfall, so then we can understand much precisely or much accurately that how the rainfall is varying in the space or in the time in that area, right? So because for that we need to have a good gauge network or rain gauge network. So in India there are more than 700 rain gauge stations, based, it can be state or central. Then based on these stations, IMD or Indian Meteorological Department gives us the gridded precipitation data. Precipitation data is given at around, minimum is 0.25 degree and 0.25 degree, that is around 28, 28, yeah, 0.25, sorry, 0.25 degree by 0.25 degree, it will be around 28 kilometer by 28 kilometer. And the temperature is also given by IMD at around 1 degree by 1 degree grids. Okay. So yeah, so for that we need to also know that how many number of rain gauges is optimum for a given area. Okay. So to estimate that what is the optimum number of rain gauges in a network, we just use this formula, that is n is equals to cv by epsilon whole square. Okay. Where n is the number of optimum rain gauge that should be present in the area. Okay. And this CV is the coefficient of variation of rainfall in existing rain gauge network, and this is in percentage. Coefficient of variation we should know, because coefficient of variation is written as sigma m minus 1 by p average into 100 because we need in percentage. This sigma m minus 1 is what? It is the standard deviation, that is sigma m minus 1 equals root over pi minus p average square summation divided by m minus 1. And m minus 1, when we do for when we have a sample estimate. Okay. And p average, or let's say p average, I'm writing as p bar, it will be 1 by m summation equals to 1 to m pi. Okay. So from there we can know the coefficient of variation. This epsilon is the allowable error that you want. Like you can mention that, okay, this much error we can allow, so that will be the allowable percentage error in the estimation of mean rainfall of the region. Okay. From this we can estimate that how many number of rain gauge is at least required for, let's say, a catchment or for a region. Okay. Now this precipitation can be measured as we have seen from the rain gauge or the manual. Then we can also use satellite estimates. We can use radar for estimating the precipitation. So the radar is what? Radar is radio detection and ranging technique. Okay, so in this works on the principle of reflection of energy. So let's say if there are water molecules are present. Okay, so in this radar, what happens? Microwave frequency will be emitted from that. Wherever this radar stations are there, microwave frequency will be transmitted into the atmosphere, and then if a beam hits the solids or liquid particles that is present in the atmosphere, it will that and will reflect back, right? So the intensity and frequency of the return signal and the elapsed time from the transmission of the signal will be measured, and from there we can determine the how much amount of rainfall is there, what is the intensity of rainfall, and from, because we'll know the elapsed time from going from here or the station and coming back to the sensor, right? So we'll know it by reflectance. What is reflectance? That is the fraction of the reflected energy. Okay, so the reflectance, we have seen that it is Z equals to A R to the power B, where R is the precipitation, and so on. Okay, other than radar, we have next generation radar and so on. Then we can also get the estimate of rainfall using satellites. Okay, so we have in India we have INSAT 3DR, which was launched in 2016, which helps us to get the estimates of precipitation in India. So whatever we are receiving from these satellites will be in the form of cloud imaging. Okay. So the satellites are TRMM was there. Then recently, as I said, INSAT 3DR is there, and so on. Okay, I'm not going very deep because that is explained in the lectures. We'll just do some questions first, and then we'll move again. Yes. Yeah. So the next question is, how many types of rain gauges are there? So as we have seen, there are two types, that is non-recording and recording type of rain gauges. Hence the answer will be B. Okay, next question is, dash is a non-recording type of rain gauge. So answer will be, so whatever first one is weighing bucket type, that is one of the recording type rain gauge, right? Second, tipping bucket is also recording type. Third, that is floating or natural siphon type rain gauge is also one recording type of rain gauge. So answer will be Siemens rain gauge. Okay, so answer will be D. Next question is, which of the following term is not used to designate a rain gauge? So anemometer. So this anemometer is used for wind lead and all. So this pluviometer, ombrometer, hyetometer, these are related to water or related to rainfall. Hyetometer you see, hydrometer you see in the satellite estimates or radars. These all will be related to rainfall, but the anemometer is not used to designate a rain gauge. So correct answer will be A. Next question is, rain gauge density is defined as the ratio of. So what is the rain gauge density? Rain gauge density is how much dense is the rain gauge network in one area. So rain gauge density is defined as the ratio of total area of the catchment to the total area of rain gauges that is present in the catchment. Okay. Next question is, which of the following is an advantage of using satellites estimates of precipitation? Right. So as we have seen, by satellite estimates we do the real-time monitoring, that how much is the estimate of precipitation right now. Around, there will be some lag, 5 minutes or 15 minutes. So that is the main advantage of using the satellite estimates of precipitation. Okay, so correct answer will be B. Okay. Next question is, the mass curve of rainfall is a plot. Okay. Okay, so before going to the mass curve and all, now we know that how the rainfall is measured using on ground, using manual technique, or using satellite estimates or radar and so on. Now we have measured the rainfall. Now what to do? We should use this data, or the data that we have measured. We should use this data to analyze and to get to some of the conclusions, right? So what we are going to do with this data, we are going to analyze this data, and hence will represent this rainfall data in some form, and then we will get or infer some of the information from those data, right? So first one is the mass curve. So first one, to present this data, we have mass curve. What is mass curve? Mass curve is the plot of accumulated rainfall, which can be in millimeter, let's say, accumulated rainfall with time on the x-axis, can be in hours. Okay, so let's say in the first hours rainfall has started, it will go like this, and after some point rain has stopped, so it will just go like this straight line. Again after some time rainfall has started, so it will again go like this, and again after some time, let's say, rainfall has stopped, so it will go like this. Okay, so here one event has occurred, one rainfall event has occurred, here one second event has occurred. Okay, and in this straight line, in the horizontal line, what we have no rainfall, and hence it is going just horizontal. Okay, so this how we get records of, let's say, a weighing bucket type or siphon type. As I said, there is one clock time mechanism where the charts itself prepares this mass curve. Okay, then we have hyetograph. What is hyetograph? Hyetograph is the plot of rainfall intensity. Intensity, as we have seen, unit will be around millimeter per hour or something like that, in and in time. So this hyetograph is a bar plot. So let's say first 8 hours it has happened around some intensity, let's say 0.2, 0.4, 0.6, something like that. Okay, in the next 8 hours it is something like this, and something like this, something like this, something like this. Okay, so let's say first one is the 0 to 8 hours, second one is 8 to 16 hours, 16 to 24 hours, and so on. Okay, so this one is the bar chart representing rainfall intensity versus time. Okay, and this has been derived from mass curve only. So now each of the bar plot that you can see, this will represent the, or the area of this bar will represent the amount of rainfall that has happened during that duration. During that duration as in 0 to 8 hours. Okay, rainfall occurred in that hour. Okay, next we have depth area duration curve. Depth area duration curve. Okay, so this is the plot between average rainfall depth, which can be in millimeter, centimeter, whatever, and in this it will be area, let's say in kilometer square, and there will be several duration. So for each duration you will have one curve, let's say 6 hours, 3 hour storm, or 2 hour storm, something like that. Okay, so from this also we'll get the areal distribution characteristics of a storm of a given duration. And what we can see for any of the curve, what we are seeing, that for a rainfall of given duration, the average depth, so here you can see on the y-axis it is depth, and on the x-axis it is area over which the rainfall has been distributed. For each of the curves, what we can see, that the average depth will decrease with the area. So as the area increases, the average depth will decrease, and that too in an exponential fashion. So if you see empirically, it is around, let's say, average rainfall is p bar, that is equals to p naught into e bar minus k e bar n. Right, this k and a and k and n are coefficient. A is obviously the area, and this negative sign is why, because with the area the depth is decreasing, and e is because it is exponentially decreasing. The p naught is the highest amount of rainfall that happens at the storm center. Okay, so this is how we represent the data. or the rainfall data. Now we should have consistency of the rainfall records. Otherwise, let's say if what today I am measuring the rainfall, and after maybe 10 days we are measuring the data, and again after 20 days we are measuring data. This 10 days, 20 days we don't have data, and it will be very difficult for us to know or get any inference from that. Okay, so the data should be consistent. And how we will know that whether the data we what we have is consistent or inconsistent, and what we can do on that. So consistency of data you can understand. Now we have this inconsistency of data we can understand. Inconsistency of data you can understand using the double mass curve. What is double mass curve? Double mass curve is the plot between the cumulative average annual rainfall of neighboring stations, okay, and in the y-axis it will be cumulative annual rainfall of the station, okay, and it will be in reverse chronological order. So if let's say we have the annual data from 1990 to 2010, so it will be go from 2010, then 9, 8, 7, 6, 5, like that. Okay, so what we see is, so let's say if there is no inconsistency in the data, this inconsistency, why it can happen? Let's say if you are changing the instrument, if you are changing the environment surrounding the environment, let's say forest was there, or there was a there was no structures in the area for that rain gauge. Now there are some buildings across the rain gauge, then it can change the consistency of the data. Then again, let's say if you have changed the gauge rain gauge location, then also it can have inconsistency in the data. Now what we do, if let's say there is no inconsistency in the data, then the plot should go on the 45-degree line, right? Now let's say you start from 2010, 2009, and something like that, and up in around 2000, let's say in before 2000 or in the year 2000, you have changed the location of the rain gauge. Okay, so from 1990 the rain gauge was at this position, okay, and you have shifted the rain gauge to some distance far from this location. Then what can happen, the data can have inconsistency, and because of which this line can go in other direction. Okay, so here comes the inconsistency. So how we can come to the consistent data? We'll just take the slope of this, okay, and we'll know the slope of this, let's say y and x. So just applying the correction factor, the correction factor equals what? The slope, let's say this is O, this is point A, this is point B, and this is point C. So the correction factor will be slope of OA divided by slope of AC, right? So now with that will be correction factor, and that will multiply with the inconsistent data to get the consistent estimate. Okay, so these were the inconsistency of the data. Okay, next we estimate the mean annual rainfall. Okay, so why we do mean annual rainfall? So what we do, we have point rainfall data, right? Now we need to know what is the rainfall characteristics over a region or over a let's say catchment or watershed. Then what we do, we convert this point rainfall at various stations into average over a basin or average over a catchment, let's say. So for that we go for this estimation of mean annual rainfall. So there are different methods. First one is arithmetic average method. So this is a very simple method, and from the name only it suggests that just take the average or arithmetic average of all the data that we have. So So there is one assumption when we use this arithmetic average method. What is that? That the area or the region, or let's say the catchment, whichever we are getting the mean annual rainfall, that should be hydrologically homogeneous. Okay, and the rain gauges are uniformly distributed. Then we apply this arithmetic average method. What we do, we just do the arithmetic average of the, so let's say Ri. Okay, so Ri is the rainfall at each rain gauge station. Okay, so just sum it up and divide by the number of stations. Okay, and from there you will get the mean annual rainfall for the whole catchment. Okay, second is the Thiessen polygon method. In Thiessen polygon method, this is also one of the method which we use for getting the mean annual rainfall over a catchment. So let's say this is a catchment. Okay, now you will consider all the neighboring stations, or whatever stations that you have, whatever in-gauge stations you have in the basin or very near to the basin. We'll consider those stations. So let's say if I change the color for this, here we have maybe one station. Here we have one station. Let's say here you have one station. Here you have one station, and let's say here you have one station. So let's say this station is A, B, C, D, and E. Okay. Now what we can see, you have 5 rain gauge stations, right? Now what we'll do, we'll connect each of the stations with their neighboring stations. Okay. So we have connected all the stations, and let's say here also one station is there, F. Okay. So we'll connect each of the stations. Okay, after connecting, what we are doing in this, we are trying to make a polygon for each of the stations, or the area which is representing for that station. Okay, now what we'll do after, sorry, now for each of the lines that we have joined, what we'll do, we'll make one perpendicular bisector of that. So for line BC, let's say this is the perpendicular bisector. For line CD, let's say this is the bisector. For E, let's say this is the bisector. For this we have, let's say this is the bisector. For this we have, this is a bisector. So from this we are getting this one, so let's say as one polygon, this one as one polygon, this one as one polygon, this one as one polygon. Again for F we have one polygon. So you can see, if you just delineate based on the station, it's a little clumsy, but for each of the station we are getting whatever the area that is contained in that basin, not outside of the basin, but that basin for that station will take that as the weight for that station. Okay, and how we are calculating the rainfall? The rainfall will be, or the mean annual rainfall will be calculated as 1 by A into summation AI into Ri, that is I equals to 1 to N. N is the number of stations that you have. Okay, so here also how we are giving the weights we are giving based on the area. So if you just open this summation, what you will see, it will be like A1 by A into R1 plus A2 by A into R2, like that. So the weight that is given to R1 is what? A1 by A, that is the area that is representing for the first station. Okay, like that. So what we are doing here, we are just giving weights to each of these. Third is isohyetal method, right? So in isohyetal method, what is isoheight? Isoheight is the line joining the points of equal rainfall magnitude. Okay. So here also, let's say you have one basin like this. So you will have isoheights. Isoheights, as I said, are the line joining equal amount of rainfall magnitude. Okay. So let's say there are different isoheights. Let's say this is 10 mm, 20, or let's say 12 mm, 14 mm, 16 mm. Let's say this is 18 mm, something like that. Okay, now for this, after getting the iso heights, we'll calculate the mean annual rainfall as A1 into R1 plus R2 by 2 plus A2 into R2 plus R3 by 2 plus divided by total area. Okay, so here what we are doing, so for, so let's say this 14 wala iso height, what we are doing, uh, area, so this area, let's say this area is, let's say this is A1, this is A2, A3, A4, A5. Okay, so what we are doing, A4 for this one, A4 into 16 plus 14 by 2. Okay, like that for each of the area we are doing. We are summing it up and dividing it by area, the total area of the catchment, and we are getting the mean annual rainfall. Okay, next is the two axis method. So in this, what we do, let's say this is the catchment and you know the outlet. So in this method you have to know the outlet. Let's say outlet is O. Okay, so what we do, first step, we draw a line which will join the farthest point of the catchment. So let's say this is one line, this is one line, something like that. Okay, so we just, so we'll join with the farthest point. So let's say this P point, or let's say T point, is the farthest point from the outlet. So we'll just join that line and then we'll draw one perpendicular bisector of that line. Let's say AB. Okay, and then we'll draw the perpendicular bisector for AB, and let's say we are getting perpendicular bisector as this one. Okay, we call it as CD. Okay, now let's say you have rain gauge stations here, maybe P1. Okay, let's say this one as P2. So what we do next, we just draw. So now this one is the major axis, the bigger one is the major axis, let's say, and this one is the minor axis, and that is why we call it as two axis method. Okay, so what we do is, so from, let's say, point P1, we join it from the farthest end of the major axis and farthest end of the minor axis. So P1, if you join P1 to D, it is a not the farthest end from the major axis, that is CD, but P1C is the farthest end, and again P1B is not the farthest, but P1A is the farthest, right? So we just calculate this theta 1. Similarly, P2D is the farthest one, and then P2B is the farthest one. This one will be theta 2. Okay, and like that we'll just calculate this mean annual rainfall again using these angles. Okay, so how you can calculate this? So this theta can be written as, so let's say what we are getting here, what we are P1A as P1AC, if you see, if you are getting one angle, so let's say ABC is the triangle, sorry, triangle, and this is the theta. You know the length of each of the line, let's say C, B and A. Okay, so how you will get the theta? You know that theta you will get as cos inverse b square plus c square minus a square divided by 2bc, right? So from there you will get the theta. Similarly, like that only, what we are doing, we are getting theta 1 as cos inverse of AP1 whole square plus P1C whole square, P1C, right? Yes, plus, sorry, minus AC whole square divided by 2 into AP1 into P1C or PC, P1C, correct. So from there we get the theta 1. So like that you have several stations. You calculate the theta for each of the stations. Okay, and then you get the weight. Weight you get as blue I is equals to theta I, that is theta for that station, divided by the total theta. Okay, I equals to 1 to n represent the number of stations. And then you get the mean annual rainfall R dash as summation I equals to 1 to n weight for each of the station into the rainfall. So let's say I was writing it as Ri, into Ri. So with this, we'll get the mean annual rainfall using the two-axis method. Okay. Now we'll do some questions and then we'll come back to the explanation. I was here, I guess. Yes. Okay. So now the question is, the mass curve of the rainfall is a plot of, as we have seen, it is the plot of accumulated precipitation against time. Hence the answer will be C. Right. Now the next question is, in a rainfall frequency chart, what does the height of the bar represents? Okay, frequency analysis we have not got yet, but in the rainfall frequency chart, frequency, what is frequency? Anyone? Frequency is like how much frequent that event will come. Okay, so here this frequency we generally denote it with probability or the chance of that frequency that is going to happen for that event. So in this, the height of the bar will represent the rainfall probability. So the correct answer will be D. Next question is, an isohyetal is the line joining equal what? Equal depth of rainfall. So answer will be A. Next question is, which of the following methods is commonly used to estimate mean aerial rainfall for a region? So what is that? Method is commonly used to estimate mean and aerial rainfall. Yeah, so for mean aerial rainfall, you can use any of the method, that is radar based estimation, be it satellite observation, be it ground based recording type or non-recording type rain gauge, like that. So answer would be all of the above. Next question is, in the Thiessen polygon method, how are the weights assigned to each rain gauge station? So as we have seen in Thiessen polygon, each of the area that is representing for that station, for the polygon of the area that is representing for that station, we consider that divided by the total area. Hence the weights is given based on the area. So right answer will be proportional to the station's area. Okay, so answer will be B. Next question is, for a catchment of monthly rainfall and the corresponding areas of influence for the stations for given below. Use Thiessen polygon method to get the average precipitation over the catchment in centimeter. So here you don't have to create all those, you know how to do the polygons and all. So polygons for each of the area for each of the polygons is given. It is that for first station it is 4 kilometers square. For second station it is 6 kilometers square. So how we were getting the mean annual rainfall using Thiessen polygon, we have seen, right? The formula was what? We have seen AI by A into Ri, right? You see that. See here, summation AI into Ri divided by A. So we'll do that only. Where was that? This one. Yeah. So you can just try once and let me know the answer. Okay, I'll just do that. So the total area, if you just calculate, it will be around. So the total area is around 249 maybe. I'll just calculate. Just calculate that. You guys also, if not today, you have not brought pen or something, please bring the pen or notebook, and so that you can do. As I said, it is a interactive session, so both of us will do, and both of us. So everything, whatever you have questions and all, you can just ask directly, or else just I'll do and you'll just see it. That will not be good, right? Yeah, it's around 249 kilometers square. Okay, so you can get the sorry mean annual rainfall as 1 by 249 into just do 4 into 30 plus 6 into 22. So this is 4 into 30, 6 into 22, something like that. plus 42 into 35 plus dot 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 up to 20 into 50. Just let me know how much you are getting. We're getting it around 8087 by 249, which will be equal to around 32.48 centimeter, because it is in centimeter. I hope you guys are getting similar, right? I hope this is clear. This is simple. You don't have to create polygons just because area of influence is given for each of the station. Just give the weightage of it. So answer would be around, it is in the range of 31 to 33. So if it is in the range of 31 to 33, you're correct. So answer is around 32.48 centimeter. Okay. So the average precipitation over the catchment is 32.48 centimeter. So that's a 32.5, let's say. Okay. Next question is the ISO heights of a monthly rainfall over a catchment is given below. Okay. So the ISO heights is given. The average precipitation over the catchment using isohyetal method is dash centimeter. Okay. So at 10 centimeter or less than that, the area of influence is 2. So let's say if I draw the catchment, and this is 10, this is 10 to 20, let's say this is 20 to 30, this is 30 to 40, 40 to 50, sorry, 50 to 60, and that's like. So this area is for less than 10 centimeter. This area is for 10 to 20 centimeter, and so on. Okay. So this ISO height, for this first ISO height, we have the area of influence as 2. So we have seen the formula. What was the formula for this? So we have seen, I'll just go through it again. See here. So it is A1 into R1 plus R2 by 2, something like that. Okay. So first we have to calculate, so not this. So first you have to calculate the average rainfall. So next, let's say you are calculating the average rainfall, or R1 plus R2 by 2. So this one will be 15, this one will be 25, 35,